And I will hand over to Aaron Schein from UMass at Amherst, who is going to be talking about Poisson-Gamma dynamical systems.
Hey, I'm Aaron. I'm a PhD student at UMass. So this is joint work with Ming and Hannah, my advisor, who's at Microsoft Research. So this paper is about modeling sequential multivariate count data. So what I mean by that is multiple sequences of counts that are related in some way. And what I want you to see here is that this data is typically bursty, okay? And what I mean by that is that the sequences, they stay low for a while, and then at a few consecutive time steps, they burst upwards, often together, okay? And then they come back down. So there's this inherent asymmetry to the dynamics of count sequences, all right? This data is everywhere. Maybe you are counting the number of times that some server is pinged in a computer network, or you're counting the number of times that a hashtag is used in a social network, or you're counting the number of times that different neurons fire in the brain. Okay, in our case, we're particularly motivated by international relations. So in this data, you observe a network of countries, and you're going to count the number of times that different pairs of countries interact. So for a given time step, we're going to observe a bunch of interactions, and then we're going to we're going to record the number of times that those the number of interactions we occurred in that vector. Okay, and we observe that vector over multiple different times. Okay, so different time steps, the vector comes in, and what I want you to observe is that a sequence of vectors we can organize into a T by V matrix, right? So T is the number of time steps, V is the number of different event types that you're tracking, okay? So I didn't make this data up. These are in our data set of country interactions, these are the number of interactions that were reported to have occurred between these 6 edges at these times. And the other thing I want you to observe is that this matrix is very sparse, right? And I've actually showed you a few edges that are relatively active in the data set. In the full matrix, there's about 6,000 pairs that have at least one reported interaction, and observed over 365 days in 2003, about only 4% of these entries are non-zero. Okay, so this is very sparse. Just some notation, y is going to be that vector that we observe over t different time steps, and it's v-dimensional. And in the general case, I think we do expect that count data is going to be sparse and bursty. Okay, especially when V is very large. So there's a lot of reasons you might want a probabilistic model. You might want it for prediction, right, forecasting future events, or smoothing, which is like imputing unobserved events that have happened in your time window. But you might want to have an exploratory task. You might want to ask some questions, like in a regression style analysis about your data. Or you might want to have an exploratory task. You might care about hypothesis generation, in which case interpretability is very important. Okay, and there's a ton of models for sequential count data already. So there's sort of autoregressive models, which are from the stats community. There's HMMs, there's dynamic topic models, and all 3 of these typically impose a sort of simpler Markovian dynamics. Then there's Hawk's process models, and these impose a more complex dynamics, but a very specific kind, where they impose sort of direct correlations between your observations, which may or may not be appropriate for your given task. And there's a huge literature on linear dynamical systems, and we like these. So these are expressive. They can express a lot of different kinds of dynamics, but they're still parsimonious. Okay, they're still sort of elegant, and that's important if again you care about these exploratory tasks, or maybe you don't have a lot of data. And they're largely based on Gaussian dynamics, and so Gaussian dynamics are very well understood. They're very well studied. Inference techniques that are in these models are therefore very mature, and they're great tools. But these models tend to be very unnatural for count data, okay? So either because they assume that the counts are themselves Gaussian, or they assume an appropriate count distribution for the counts, but they link them to sort of latent Gaussian dynamics in this non-conjugate way, okay? And, you know, this area is very mature, and so there's a lot of code, and so one option is just use them anyway, okay? And that's fine, and that sometimes that works well. But I want to make the case for naturalness, okay? So a natural model, what I mean by that is just the likelihood of the model. It matches the support of the data or other statistical properties that we know a priori for the model to have, okay? And it employs conjugate priors, you know, where it can. And these models, they tend to be statistically and computationally efficient, okay? They impose the right inductive bias, and that's going to constrain the hypothesis space, which is going to facilitate efficient inference a lot of the times. And the right inductive bias is also going to overcome a lack of data in certain cases, okay? And moreover, different quantities of interest like conditional posteriors are available in closed form in these kinds of models, or other quantities you might want to calculate if you're doing exploratory or explanatory tasks. And finally, these are important for measurement. So this is the domain in which the latent variables in your model you actually think are real things in the world, and you want to actually measure them. Okay, so in that case, it matters that your probabilistic assumptions match what you know about the data. Okay, so these are our contributions. So we have this new model, and in a relevant way, it's going to match the form of linear dynamical systems. Okay, but it's going to do so while still being natural for count data. And we present this auxiliary variable-based technique for doing Gibbs sampling. And the reason that this model hasn't been presented before is because this last step, it depends on a little bit of magic that we didn't know about until recently. So I'll show you that in a bit. And the benefits of this model are really threefold. So first, inference in this model, sort of naively implemented, is going to scale with the number of non-zeros in that matrix. Okay, and this is different than the linear dynamical system, which, without lots of engineering hacks, is going to scale with the size of the full matrix. It's going to waste a lot of time doing computation on zeros. Okay. The model is a better inductive bias. So you can check the paper. We report a series of experiments where we compare the predictive performance of the model to the Gaussian linear dynamical system and another baseline, and we show that as the data gets burstier, the relative performance of our model improves. Okay. And the model is very interpretable. I'll show you that in a second. So here's the model. A count in the matrix YVT. V is, again, some event of interest that you're tracking at t time step. So this is a count, and we're going to assume it's a Poisson, which is the natural assumption. Its rate is going to factor as over k different components. So each component is going to contribute this factor, how active is that particular event type in this component, multiplied by how active that component is at time t. Okay, a simple dot product. And the mean of this count under the model is that rate. And the interesting bit happens with this time step factor. So our prior over that is now going to be a gamma distribution, which is, again, a natural choice. It's the conjugate prior to the Poisson. And in this case, there's two parameters. The shape parameter we're going to factorize in the following way. Over every other component k prime, we multiply how active that component was at the previous time step by the probability of transitioning from that component k prime into this one k. Okay, and these are probabilities. They sum to 1. And so that links this model to HMMs and Markov chains in that the matrix pi is a stochastic transition matrix. Then there's this concentration parameter. It's a concentration parameter because the mean of theta k t under the model is the shape divided by the rate. Okay, and so tau is going to cancel on the top and bottom, and so tau is just going to control the variance, and therefore just control how concentrated the dynamics are around this mean. Okay? And so in vector form, these two expectations, they match the sort of canonical form of linear dynamical systems, right? This matrix vector product. Okay, but the model's going to do so while still being natural for count data, making the right probabilistic assumptions. So I want to show you some of these parameters that were inferred on a real data set. Again, this is going to be international relations on the year 2003. And so the most significant component that the model learned in the data, these are the relevant event types in the model, and they're dominated by this Israel-Palestine interaction event. Okay? And so then viewed in conjunction with the time step factors, we see that this component is relatively active over 2003. I'm just going to overlay the relevant event types over the action types, okay? The time step factors. So here's the second most active component, and this one spikes dramatically in March and April of 2003, and its event type is dominated by Iraq, USA. And then the third most active component. And this one, the event types aren't dominated by any single event. They are actually all of the pairwise edges between the 6 countries, China, United States, Russia, Japan, North Korea, and South Korea. Okay, so this is very interpretable. I mean, this is obviously the Iraq War. This spikes right at the time that the US and UK invaded Iraq. And this one corresponds exactly to the 6-party talk. So this is a series of multilateral relations between those 6 countries to dismantle North Korea's nuclear weapons program. And the first of those talks happens right at that spike that the model finds in August. Okay, so here's the technical challenge. This is the model. And it's slightly simplified, but it's in graphical model form, and y and theta are in their vector form as a single variable. And I've color-coded each variable. So if you're green, then you're a Poisson or a multinomial random variable, and if you're red, then you're a gamma or a Dirichlet random variable. And I want you to notice that if you are a red variable and you have only green arrows going out, then you have only conjugate relations with your downstream variables, okay? Which is good. So that's like phi in the bottom left, and that means that we can form its conditional posterior. And that's important for deriving all sorts of different inference algorithms. In our case, we want to sample from it. So we want to derive a Gibbs sampler where we're going to loop through the different latent variables in our model and sample them from their conditional posterior. Okay, and so now notice that pi in the top has only red arrows going out of it, and that's bad. That means that we can't form its conditional posterior in this model, therefore we can't sample from it, at least not efficiently. And the same is true for theta. Okay? So the high-level idea is that we're going to go from this original model. We're going to introduce a bunch of auxiliary variables. That's going to allow us to integrate out some variables in the model and ultimately get this one. And in this new model, which has some auxiliary variables, you'll notice that pi at the top has only green arrows going out from it. Okay, so in this alternate model, we can sample pi from its conditional posterior, which we can form. Okay, so how do we get from left to right? We're going to recursively use 3 different rules. 3 rules that have already been presented. 2 of them we've known for a long time, 1 that's more recent. So the first rule is the relationship between the Poisson and multinomial. So y and L are Poissons. That means that we can introduce m, which is their sum, and then conditioned on m, y and L are multinomial. Okay? Second rule is the definition of the negative binomial. Negative binomial. So m is a Poisson, its rate is theta, which is a gamma, and if we integrate out gamma, then m is a negative binomial. Okay, and I'm going to use yellow to denote negative binomial. Okay, and the next rule, and this is the magic. This is what makes it go. Okay, so here I'm showing you 2 different factorizations of the same bivariate distribution. Okay, so L and M are counts and they're conditioned on alpha and beta. And on the left, this distribution is going to factorize as follows. It's first M given alpha and beta, where M is a negative binomial, random variable. And then L given M and alpha, where L is a Chinese restaurant table distribution. And notice that L does not depend on beta in the left factorization. Okay? In the right, this same distribution is going to factorize as first L is a Poisson random variable given alpha and beta. And then M, which is a sum log random variable, and it's conditioned on L and beta. And notice that M does not condition on alpha. Okay? So in general, these 2 factorizations don't equal each other. But in this special case where with these distributions, they do. Okay? And that's going to be important. I'll show you why. So here's the original model as I defined it. And the first thing we're going to do is augment it with a Poisson. Now we're going to use rule number 1. We're going to re-represent the y and L under the multinomial Poisson. Now we get to integrate out theta 3, so m becomes a negative binomial. Okay? Now we augment with a CRT, with a Chinese restaurant table, random variable L. And now this is where we get to use this magic trick. So L3 and M3, they form a bivariate distribution conditioned on their Markov blanket. And so we can re-represent that under the alternate factorization. And I'm going to flip back and forth so you can see what's going on. The special thing is that M3's dependence on theta and pi is dropping in the latter factorization. Okay? So now once we're here, we can recurse. Now we can re-represent y and L under the multinomial. We can integrate out theta 2, so M2 becomes a negative binomial. We can introduce a CRT, and now we get to do magic again, re-represent that bivariate distribution. Okay? And then we keep recursing. And so at the end, we get a model where all the thetas are integrated out, and a model in which we can sample pi, because it has only green arrows going out of it. But on the way to deriving this model, we also derived this one, okay, in which theta 1 has green arrows going out of it, and all the future thetas are integrated out, and under this model, we can sample theta 1. And on the way to get here, we got here. And in this one, we can sample theta 2, conditioned on theta 1, but with all the future ones integrated out. And similarly, we can sample theta 3 under this model, okay? And so in other words, we get this backward filtering forward sampling algorithm for thetas, okay? Backward filtering step is we introduce the auxiliary variables from the end of the chain going back to the beginning and interleaving the marginalization of theta. And then going forwards and conditioned on those auxiliary variables, we can sample each of the thetas, conditioned on the previous thetas with all the future ones integrated out, okay? So in conclusion, we get this elegant inference algorithm in the natural model for sequential counts. It scales without any hacks for the number of non-zeros, okay, in the matrix, and it demonstrates a sort of novel auxiliary variable scheme. Thanks.
Thank you very much. There's time for questions.
Quick question here.
Oh, over there.
Hey, Aaron, very nice talk and work here. I just had a question. Do you know what the marginal distribution of the observations is?
No.
Okay.
You mean the Y's?
Yeah.
No. You mean with all the variables integrated out?
Yeah, like in a linear Gaussian model, you would have that. In other time series models for Poisson counts, you can get Poisson margins.
Yeah, yeah. No, this is the cost I think you're paying. So and as a result that you don't know the marginal. The nice thing about in the Gaussian linear dynamical system is you have filtering forward in a really nice way, and you don't get that here. So this is really like a retrospective model in the sense that you have to start from the end of the chain. You have to really define the end of it and integrate backwards. And so I think it's hard to define that marginal. Yeah.
There's a question over here.
Hi. So I was wondering, so the model that you end up with, if you look back at it, so does it have a natural causal interpretation?
You mean a causal in the sense of the y's now have an arrow going forward?
Yeah, you introduce these new variables, and you have these arrows flipping directions.
Yeah,
maybe it sort of makes sense as a.
No. So in the original model, it looks like an HMM. So the y's are all conditionally independent given the latent structure. When you integrate out the thetas, suddenly these arrows appear. Each y feeds back into the system. Okay, and I think that's where the burstiness. That's why this model represents burstiness, because some counts go down to y, and then if not enough counts go down to y, then the sort of remaining counts get sent back into the system, and so the system builds up. But I agree that there's a lot of interesting interpretations in terms of which version of the model you use. I haven't explored the causal question.
Thanks.